Okay, it's 7:55, so let's go ahead and get started. For bell work today, you have the choices on how you want to do this one. G W W F J Q. Bo, 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 bo. So you could solve this system traditionally, or using Kramer's rule and finding your determinants, or using a calculator and doing the inverse matrices. So I'll give you 3 minutes to use whichever method you like, and then we'll go over it. Almost sneezed, but I didn't. Okay. So as I said, there's a lot of different ways that you can do this problem, and it doesn't matter to me which method that you use for the test. I believe it's just going to set up the problems like this. We're going to say solve the system, and so you won't have to use a particular method at any point. So how I would do this, and I think would be good to review, is the method we just learned. So if I stop share really quick, reshare the whole screen, put this up along with the calculator. The easiest way that I would think would be to do this is to use the inverse matrices rule. So I'm going to go into my matrix. I'm going to redefine matrix A to be a 3 by 3 with coefficients 1, 2, -3. 0 for 2, right? There's no x value for this one, so 0 for 2. And then -1, 1, -1. -1, 1, -1. All right, if I go back in and define matrix B to be a 3 by 1 with constants -28, 0, and -5, I can then, there we go, perform this operation. I want to take matrix A, I want to do its inverse, which is this key right here, and I want to multiply that by matrix B. And there you go. Answers are x is -4, y is -3, and c is 6. Questions on the bell work? Okay. All right, then we're going to do the last lesson here in chapter 7, matrices and systems of equations. So this is showing you one final way to solve a system of equations using matrices. This last application is probably not the most useful for finding systems of equations, but it does have applications beyond that. Like it's a different way that you can find inverses if you really want to. But it's not that bad. I don't know. You'll see. It's basically taking that 7.3 chapter and doing that Gaussian elimination system, but using a matrix to format it instead. So really, there's nothing actually new you're learning per se. It's just a different format. So we're going to learn how to do two things today: how to perform elementary row operations on matrices, and then to use matrices and the Gaussian elimination method to solve systems of linear equations. So first, To do that, to use Gaussian elimination, you need to know how to do two things. First is how to write an augmented matrix. An augmented matrix is a matrix that's derived from the coefficients and the constants from a system of linear equations. So if you have this system right here, I'll place my coefficients in the first three columns: 1, -4, 3, -1, 3, -1, 2, 0, -4. And then I use this like breaker. The book uses 3 dots for this, but I've also seen it commonly as just a vertical line. To be honest, I've seen it more as just a vertical line than I've seen it with these 3 dots. But you just have some visual indicator that this last column, which is your constants, represents a different sort of those numbers represent a different sort of thing than these numbers over here. These numbers represent the coefficients. These numbers represent the constants. And to be honest, this is purely visual. It actually has no impact on our math whatsoever, as we're going to run through these problems, whether or not this demarcation is here. All right, once you have your system converted into a matrix, you then can perform the following operations on it to try to solve it. There are 3 operations that are valid. The first is that you can interchange 2 rows. The second is you can take one row, multiply it by a number, and then add it to another row. Or sorry, I'm getting ahead of myself. You could multiply it by a number and just change it that way. And at C, you could also take a row, multiply it by a number, and add it to another one. So those are the only 3 operations that you're allowed to do. Then we're going to solve, like, try to change the matrix so that it fits a format that we could then easily pull the answers from. All right, so I'll give you a minute to finish up writing on this slide, and then I think how this is going to work, there's be 2 examples, a guided practice, and then we're done. Okay, does anybody need more time, or are we good to go? Okay. Oh, wait, what? Interesting. Okay. All right, so to solve this system using Gaussian elimination, this is really going to test my ability, because Gaussian elimination is not actually that hard to do. It is a little bit tedious, and it takes up a lot of space. So we're going to see if I can get this. Let me see if I can just try to demarcate some stuff oh, to try to help me be organized because we're going to need a lot of space. All right, so first thing I'm going to do is change this to an augmented matrix. So my first line will be 1, -2, 3, 9. And then -1, 3, 1, -2. And then 2, -5, 5, 17. So that's my augmented matrix. Again, these are my coefficients, my x coefficients, y coefficients, z coefficients. This is my constants column. I put my first equation here on the first row, second equation on the second row, third equation on the third row. All right, here's your goal. Your goal is to transform this so it looks like this. Okay, where I don't know, these x's are all different numbers. They're not all x, but this is what I care about. I want there to be ones along the diagonal and zeros in the bottom left or right corner. That's my goal. Because once I have this last equation with only one z equals a number, I can then take that number and plug it in to this equation to find out what y is. And then I can take y and z and plug them in to find out what x is. Or, so that's one way I can finish out the problem. Is once I have it like this, I could use what this is called as back substitution to take my z solution, use it to find y, take y and z to find x. Or the other option is once you have it like that, you can keep going and eventually get it to look like this. And then you'll be able to get x, y, and z just from reading the column. So you can either back substitute or continue your elimination to fill the rest of this with zeros so that you have 1x equals whatever this number is, 1y equals whatever this number is, and 1z equals whatever this number is. All right, so that's the most important thing. Most of the people that got lost in this section last year got lost because they didn't know what the goal is. This is the goal. First, to get ones in the diagonal and zeros everywhere else. So if I start, I need this number to be a 1. Hey, it is a 1. All right, so then what I'm going to do is I need these two numbers to be 0. So to do that, I'm going to use this operation, this last one. I'm going to multiply my row here, my first row, and add it to the others to get them to be 0. So if I take row 1 and I multiply it by 1 and add it to row 2, that'll change this to a 0, right? 1 times 1 plus -1 is 0. To get this 2 to be a 0, I would need to take row 1 and multiply it by -2 and add it to row 3. So this is row 1 times 1 added to row 2. Row 1 times -2 added to row 3. If I perform these two row operations, the next matrix I would get is 1, -2, 3, 9. I'm not actually changing row 1. I'm only changing row 2 and row 3. All right, to get my new row 2, I'm going to take 1 times 1 plus -1, which is 0. I'm going to take all, and I have to do this not only for the first column, but all of the columns in row 1. So I'm going to take -2 times 1, which is -2, and add it to 3. That's convenient that changed that to a 1. All right, I'm going to take 3 times 1, which is 3, and add it to 1. I'm going to take 9 times 1 and add it to -2. So that's 7. All right, to get my new row 3, I'm taking all the elements in row 1, multiplying them by -2, and adding them to the elements of row 3. So 1 times -2 is -2, plus 2 is 0. -2 times -2 is +4, plus -5 is -1. 3 times -2 is -6, plus 5 is -1. 9 times -2 is -18, plus 17 is -1. That's kind of weird. All right. Any questions on what we're doing so far? Okay. All right. So I've got my first column looking how it's supposed to look. I'm now going to start working on the second. I need this number to be a 1. Hey, it is 1. Great. I need this number to be a 0. Hey, it's not 0. Okay. That's not a problem though. How I'm going to fix that is I'm going to take row 2, multiply it by whatever number I need. So when I add to row 3, I get 0. And I believe that number would be +1. Row 2 times 1 plus to row 3. Right? If I did 1 times 1 and I add that to row 3, that would get -1 plus 1 is 0. Again, which is what I want. That's the goal. All right, so I'm going to go ahead and do that. This time, the only row that's changing is row 3. So I'm just going to copy my first 2 rows. 1, -2, 3, 9, 0, 1, 4, 7. All right. The reason why I go one column at a time is I think you're about to see, because when I do this, 0 times 1 plus 0 is 0. Right. Now that these are set, this first number won't ever change from 0, which is good. I want it to be 0. All right. If I take 1 times 1 plus -1, that's 0. 4 times 1 is 4, plus -1 is 3. 7 times 1 is 7, plus -1 is 6. Any questions about how we got this next matrix? Okay, then I've now done with the first 2 columns. The last column, I need this to be a 1. It's a 3 right now. So to fix that, I will multiply it by a third. Basically, I'll divide it by everything in this row by 3. That way this gets turned into a 1. Again, row 1 and row 2 are not going to change. The only thing that's changing is row 3. Okay, so if I divide both these numbers by 3, I get 0, 0, 1, 2. I have now accomplished my goal. I now have a choice in how I want to finish out this problem. I can use a back substitution, or if I keep going to make these numbers 0 and this number 0, then I would be doing what's called Gauss-Jordan elimination, and that would be fine. I'm going to show both of them to you because Mr. Lake is that generous of a teacher. All right, I'm going to do back substitution first. So what this tells me basically is that 1z is equal to 2. Oh, here, let me rewrite the whole thing. Let me rewrite the whole thing for you. So what this is now telling me is that this first row is telling me that 1x minus 2y plus 3z is 9. This second row is telling me that 0x plus 1y plus 4z is 7. And then this last row is telling me that z is 2. If I plug that back into this, what I'll get is that y plus 4 times 2 is equal to 7, which means y plus 8 equals 7. Which means y is negative 1. If I now plug z and y into this first one, I'll get x minus 2 times negative 1 plus 3 times 2 is equal to 9. Which means x plus 2 plus 6 is 9. Which means x plus 8 is 9. Which means x is 1. So there you go. I have my solution. These three linear equations intersect when x is 1, y is negative 1, and z is 2. All right, I'm going to erase this to show you what the Gauss-Jordan elimination method would look like. So does anyone have any questions about just this part? Or needs more time to write? Or I could just do it up here. I mean, I don't think we should need this anymore. Yeah, I'm just going to erase this top part. We shouldn't. Nope, I don't want to. That way you can see the whole thing from start to finish. All right, so anybody need more time to write this back substitution part down? Okay. All right, so the other way I could finish out this problem is to try to make it look like this, using continuing to use Gaussian elimination. This is actually called the Gauss-Jordan elimination algorithm. So now I'm going to go back and make these numbers 0. And again, I'm going to use row 3 to do this. That way the zeros won't mess up anything in the first two columns. Because I still want this to be a 1 and I still want this to be a 1. I just want to mess up these two. So I'm going to do row 3 times negative 3, and I'm going to add that to row 1. And I'm going to do row 3 times negative 4 and add that to row 2. That should get me a 0 here and a 0 here. So if I do that, again, the first two columns won't change. Because 0 times anything added to something is just itself, right? This is just adding zeros to the top two rows. All right, over here, the bottom row doesn't change. Okay, so now if I do, let's do this first row. 1 times -3 is -3, plus 3 is 0. 2 times -3 is 6, or -6, plus 9 is 3. 1 times -4 is -4, plus 4 is 0. 2 times -4 is -8, plus 7 is -1. All right, you see I'm almost done. The last thing I need to change is I need this -2 to become a 0, and I'm going to use row 2 to do that. So I'm going to take row 2, I'm going to multiply it by +2, and add that to row 1. So boop, 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 boop. All right, 1 times 2 is 2, plus -2 is 0. 0 times 2 is 0, plus 0 is 0. -1 times 2 is -2, plus 3 is 1. And here you can see we got the same answers that we did before. X is 1, Y is -1, Z is 2. All right, does everyone, by the way, see where I got this 2 from, where I got the -3, where I got the -4, where I got this 1, where I got this 1, and where I got this -2? It's always just the opposite of whatever number you're trying to eliminate. See that? Opposite of -1 was 1. Opposite 2 is -2. Opposite of -1 was 1. Opposite of 3 and 4 was -3 and -4. Opposite of -2 is +2. So it's always just the opposite of whatever you're trying to make into zeros. Questions? Does anybody need more time on this? Okay. I want to make sure you get a chance to try this on your own before we go. So I think I'm going to make this example. Who do I want to? Yeah, I think I'm going to make this example into our guided practice. So I'll give you 4 minutes on this one. So at 8:30, hopefully you'll be done or getting close to done with solving this one, and then we can go over it. So 4 minutes, please try to solve this using the method that we just learned. Remember, your goal is to get this into 1, 0, 0, 1, 0, 1, where whatever these other numbers are is fine. And then after that, you have options. Okay. So to get started on this one, first thing you'll want to do is change this. 1, -1, 2, 4. 1, 0, 1, 6. 2, -3, 5, 4. All right, can anyone tell me in chat what the first row operation I would do is? Or unmuting is fine too. What think was the first thing I would do? To make these 0, the 1 and the 2.
Multiply the first row by -1 and then add to row 2.
Yeah, that's right. So I'm going to do -1 times the first row plus the second, and -2, first row, added to the third. Now get 1, -1, 2, 4. All right, so then this will be 0. -1 times -1 is +1, plus 0 is 1. Hey, that's great. 2 times -1 is -2, plus 1 is -1. 4 times 1 is -4, plus 6 is 2. For my third row, 1 times -2 is -2, plus 2, 0, which is great. That's what we want. -1 times -2 is +2, plus -3 is -1. 2 times -2 is -4, plus 5 is +1. 4 times -2 is -8, plus 4 is -4. All right, this is a 1, so we actually are already good to go. How do I make this a 0? Oof. Y'all are scaring me a little bit here. It's just the opposite of this number. +1. Well, there we get. Are you just tired? I can understand just being tired. I think I've gotten 4 hours of sleep in every night for the last 3 nights. All right, 1 times 1 is +1, plus -1 is 0. -1 times 1 is -1 plus 1 is 0. Uh-oh. And then 2 times 1 is 2 plus -4 is -2. This means that 0 equals -2, but that can't be true. So that means this has no solution. And you don't even need to finish. Right? If you wanted to try to finish this, there's no way I could multiply 0 by a number to make it into a 1. So this problem has no solution. All right. You have the last assignment in WebAssign for this semester for 7.4. Thursday is going to be a review day, and then you'll have all week from Monday till Friday to turn in the test. So try to complete the homework before Thursday. Thursday will be a work day, review day, and then next week is the unit test. And then that's the end. If you run into any problems while you're doing the homework, let me know and I'll help you out. But otherwise, have a good rest of your day, everybody. See you Thursday.